In this video, we're going to picture another way, I think, which maybe is going to be more tangible and will help us as we kind of build in a little bit some more numerical methods to solve 2D conduction. So the method that we discussed together in class was really a method founded on kind of the math of the numerical solution to this differential equation. So this is a second order differential equation depending on both x and y. And what we did is we used mathematical methods to take this and make it from a differential equation. We discretized it. We made it, instead of delta x or dx and dy, we transformed it into an equation like this based on delta x and delta y. That was a method really founded on kind of on mathematical principles of numerical methods, like numerical solutions to this equation. What we're going to do in this video is look at a different method to think about the same thing, which I think, again, will help us hopefully get a better grasp around what's happening and where these equations are coming from. So method one, again, kind of starting from the heat diffusion equation using numerical methods. Method two, we're going to look at this equation and realize that, so this came from an energy balance. So we're going to look and see how can we build up the same understanding by, instead of looking at this equation and solving the equation numerically, let's look at the discretized problem, right? The problem where we've diced everything up into little boxes, and then let's look at doing energy balances for that problem. So what we're going to do is choose a grid like this, right? So these are our discretized points. What we're trying to do is not find the temperature everywhere. What we're trying to do is find the temperature at these individual points. These are just 9 points in our object. What we can think of is having really diced up this section into a grid, something like this. So these go, those kind of continue on. Something like this. So we can think of each of these individual points, like point MN, really is representative of this entire chunk of our material. What we're saying is that this is it's a small chunk, but this entire chunk of material has one constant temperature. So this entire CV, control volume, this is our control volume MN, has temp T MN. So again, this is a small chunk. It has dimensions delta Y and delta X. And it has a temperature TMN. When we're looking at this, we're going to be looking with really two different principles. So we're going to be looking at heat moving from the surrounding control volumes into the center. I'll erase my delta X and delta Y for right now. We're going to be looking at heat going from, say, this one at the bottom, transferring into our control volume. From the side, we're going to be transferring in from that guy to the middle. We're going to be looking at heat going in from that side and in from the left side. We're going to be doing this just as really a sign convention, a way to handle the directions. We're going to always assume that, okay, heat is always going in. And our energy balance is going to say that the change in thermal energy inside of our control volume, right? So the change in energy inside of our box, TMN, or inside of our box MN, is related to like how much thermal energy came in. So if 1 unit of thermal energy came in, the change in thermal energy inside the box is 1. Right, fairly simple. And that works. That's just a restatement, kind of a simple restatement of conservation of energy. Let's look at just one section of our box. So again, we'll look at this box, Mn, and we'll look at its left-hand neighbor, M-1n. So we're going to be looking at heat going, we'll call this Q left, because it's on the left-hand side. That's going to be how much heat is going from that box, Tm-1n, into our center box, Tmn. Just to note a couple things about this, right, we have side length, delta x, that's delta x. This side length is delta y. As we look at how we can think of the heat transfer, right, Q equals minus K dt dx. So this is heat transfer in the x direction. So this is going to be what the temperature is. Those boxes have a side length of delta x, but we can also say, like, from the center of this box to the center of our other box, this is also, that dimension is also delta x. So Q left is approximately equal to minus K. So what is the slope of the temperature? Well, the slope of the temperature is going to be the temperature on the left-hand side minus the temperature on the right-hand side divided by that distance. So that's our estimate for the temperature. So this is, again, approximately equal to Tmn minus Tm minus 1n, right? Right-hand side minus left-hand side, all over the distance delta x. Again, this is our discrete representation of what we're actually trying, the equation we're actually trying to look at up here. Okay, that is would be what we would call Q prime. So this is the per area version. So the total heat into the left side, which is Q left, that equals the area, delta y, times Tm minus 1n minus Tmn divided by delta x. And basically what I did is I took the negative sign that was in that equation before and multiplied that through, which switched Tmn and Tm minus 1n. Right, this is our area that conduction occurs over. So that's our area, right? That's this, the length of this side is delta y. The length of the side between those two boxes is delta y. So if we look at our total energy balance, so if we look at all four of those sides, we could say that the change in stored energy in our box is equal to Q top plus Q left plus Q bottom plus Q right. At steady state, the change in stored energy in our box is 0. The temperature is not changing. Right, that's how our object is going to be storing energy. It would be a temperature change. So we could write that 0 equals, okay, so we'll write Q top. So Q top would be, again, coming back to this picture, it would be the heat coming in at this top surface from T m n plus 1. This would be K T m n plus 1 minus T m n. The area of that side is delta x. So this is delta x times K divided by delta y. Now Q left, which is the one that we wrote before, that's delta y times K times T m minus 1n minus T mn divided by delta x. And I'm realizing I dropped a K up there. So that's the top, the left, could add the bottom. We'll add that down here. Plus at the bottom, that's going to be delta x, K, T, m, n minus 1 minus T, m, n divided by delta y, plus now the right-hand side should be delta y, K, T, m plus 1, n minus T divided by delta x. So a few things. K divides out. If delta x equals delta y, then delta x over delta y equals delta y over delta x equals 1. So you can see all of these terms have a K in them. All of these terms have either delta x over delta y or delta y over delta x. But if we choose that, so delta x and delta y are the same, say 2 centimeters, then those will divide out and just be equal to 1. So that would give us 0 equals T m n plus 1 plus T m n minus 1 plus T m m plus 1 n plus T m minus 1 n minus 4 T m n, which is the exact same equation that we got when we, like, just the average of the 4 surrounding temperatures, the exact same equation that we got when we looked kind of from a more mathematical standpoint at what this center temperature is going to be. But I think this is just, again, another way to think about the problem, looking at it really from an energy balance standpoint, that we have energy transferring into that from all of the surrounding spaces. This will help us as we look at how we can think about boundary conditions.